Today, good morning dears. Today we are here with Haloalkane Haloarene previous year question from 2024 question papers. That is the January shift as well as the April shift. We are here with questions or mostly all the questions from Haloalkane and Haloarene chapter. First, we'll be doing the question. I have taken few many questions. So we'll be doing with the questions. So the first question is here on the screen. You can read, you can pause the video and solve, and I'll be explaining it. Okay. Yes. So given below are two statements, one labeled assertion and another labeled reason. Haloalkane react with KCN to form alkyl cyanide as a main product, while AgCN form isocyanide as main product. KCN and AgCN both are highly ionic compounds. Listen here. The first assertion, look, haloalkane react with KCN to form alkyl cyanide as main product, while AgCN form isocyanide as main product. In your NCERT textbook, I'll show your NCERT textbook. Yes, sorry. In your NCERT textbook, it is clearly written that KCN being an ionic compound, I don't know, this color is visible. Let me change the color 1 second. Because I can't write white on white. Anyway, I'll write with red itself, that's better. Blue is there. It's better. No, red is better. Okay, anyway. KCN is an ionic compound. It's given in your NCERT. As KCN is an ionic compound, what happens is that KCN can donate both C and N. KCN can donate both C and N for bonding, and hence carbon bond is stronger. What happens? Yes, CN bond is formed. That is carbon. That's cyanide is formed. It's given in your text because KCN is ionic. We can get Cn minus as a free ion, and the Cn minus go and attach with carbon. It can use nitrogen as well as carbon for sharing, for forming bond. But carbon bond is stronger than carbon nitrogen bond. Hence CCN, that is cyanide is formed. But AgCN is covalent in nature. It's given in your textbook, covalent. So therefore the reason is given AgCN and KCN both are ionic. So this reason is wrong. AgCN is covalent in nature. Hence AgCN can only give, because AgCN can only have AgCN. This is the form. Carbon is attached to this Ag. Hence carbon is not free for bonding. Only nitrogen is what? Free for bonding. Hence what happened? Hence nitrogen will go and attach with carbon, forming CNC. That is what isocyanide. So we get RNC. Okay. So when we use KCN we get cyanide, and AgCN we get isocyanide. The reason is that KCN is ionic and AgCN is covalent. So here reason is wrong, assertion is correct. So assertion is correct, reason is not correct. One is the answer. Okay. Yes. Next we have this question. You can do it yourself. So you can pause and do the question if you need. Now we have this question. Identify A and B in the following reaction. First A. 1 second, sorry. Sure. Yes. A. Look, it's just very simple. A. Cl2 we added to this toluene. Toluene press Cl2 in presence of H mu, we get benzyl chloride, that is CH2Cl. So this is not the answer. So we are having 3 options that can be right now. When we react this with H2O in 373 Kelvin, we get. Anyway, this is not the answer, and this is also not the answer. Okay, second one is the answer. No, third one is also. 1 second, what's happening here? My God, something happened. I will do once again. Something went wrong. Yes. Sorry. Okay. Look here. We are having this compound CH3. Now, when we react this with Cl2 in presence of H mu, we get benzyl chloride. Okay, benzyl CH2Cl. So this third option is correct. CHCl, CHCl2. Second is wrong. Second option is wrong. First option is wrong. So third or fourth. Now when we react this thing CH2Cl with the H2O in 373 degrees Celsius, what we get? We get benzaldehyde. So option 3 is the correct answer. Okay. Yes. Now we have this question. 1 second. Yes. So here it is C2H5Br plus alcoholic KOH. Alcoholic KOH means what happens? Yes, there what happens? Yes, double bond formation, bromine elimination reaction. So we get first of all I'll draw the structure of this thing. That will be easy for me. CH3CH2Br. What happened? This bond falls here. So we get CH3CH2 double bond. Yeah. Sorry, children. Sorry. CH2. We got this. Now we are adding Br2 and CCl4. We get what? Cyclohalonium. Intermediate is there. We get what? Geminal or vicinal? We get vicinal dihalide. Yes. Br. This thing is formed. Now we are adding excess KCN. Okay. Let me check. I don't know if this will be correct because first time I am seeing this questions itself. I think what I am writing. When we add KCN, what's happening? KCN, here cyanide ions are there. So cyanide. Now at last, okay, this thing is here. Now what we are having? We are doing CH2, COOH. I think this will be the answer. 1 second. OMSGAP. Oxalic acid, malonic acid, succinic acid. So oxalic means 2, malonic 3, succinic acid is here. Yes, so I think succinic acid is the answer. Apo succinic acid is the answer. Okay, I hope you understood. It's simple question. We can easily do it. What this Ohm's gap means? It is oxalic acid, malonic acid, succinic acid, gluconic acid, adipic acid, and picric acid. The order for the acids I usually learn like this. And at last what happened here? H3O plus means hydrolysis of cyanide. It is there in your carboxylic acid chapter. Somewhere it is given. Preparation of carboxylic acid from cyanide. It's given in that chapter. Okay. Page number. 1 second. I have my book with me. I'll just check and tell you the page number. 1 second. Sorry. Yes. Page number 246 of your chemistry part 2 textbook. You have the same. Okay. So next question is here. I'll just copy paste. 1 second. Yes. This will be the next question. Yes, you can read. The correct statement regarding nucleophilic substitution reaction in a chiral alkyl halide. Retention occurs in SN1 reaction and inversion occurs in SN2 reaction. You look, SN1 reaction means what? Carbocation, racemization, Okay, I learned like this. SN2 reaction. What? Transition state. In SN2 reaction, the thing is that it's having a transition state. I'll take an example of this thing that I itself taught in my haloalkane part 1 class. Look, here OH is going, X is coming. If X is coming through the same path the OH, if X is coming like this and OH is leaving like this, what problem is that there will be what? Repulsions. It can't happen. Repulsions can't be there. It is what? Impossible for repulsion. Hence what we'll do? Repulsion should not happen. So what we'll do? X will only come and join to the opposite side. Hence we get the inverted product. The same thing we told in SOCl2's reaction also. So inverted product. So here what we get? Inversion. So now you can read the question. Retention occurs in SN1, inversion occurs in SN2. But retention, okay. No, in SN1 reaction, retention, it's not relevant. Racemization occurs in SN1 reaction. So this is wrong. Second one, racemization occurs in SN1 reaction. Racemization correct. And retention occurs in SN2. This is wrong. So this is also wrong. Racemization occurs in SN1 and SN2. That's also wrong. Racemization occurs in SN1. That's correct. And inversion occurs in SN2. That's also correct. So option number 4 is the correct answer. Hence 4 is the correct answer. Now we'll take the next question. Yes, next question we have here. 1 second. Okay. This will be a next question. A, B, C option is only there. D is missing. If D is missing also, no problem. We can get it from somewhere. D, 1 second, let me check. D option is not that important, so just we'll do with these 3 options. Okay. So which among the following halide will show SN1 reaction? SN1 reaction, carbocation. Yes. So carbocation. So primary, secondary, tertiary order of what? SN1 reaction. So tertiary first, secondary, then last. Least SN1 reaction for primary. Here look, A question. A1, you can just check A. So first of all, make a carbocation and check the stability. That's the basics of SN1 reaction. Make carbocation and check stability. First one, CH2 double bond CH2 Cl. Cl is going plus charge. Here carbocation, is it stable? Yes. Resonance. Here we are having what? Resonance. CH2 CH. Here having what? Resonance. Yes, very important. Above here it is having a resonance stabilization. So hence this is stable. So which is unstable or stable? Which of the following will not show? So this is not the answer. It will show. Now next one. CH3 CH double bond CHCl. B. CH3. 1 second. CH3 CHC double bond CHCl. CH3 CH double bond CHCl. Let me check. Now let it go. Here plus charge. Oh my god, what is this? Double bond and plus charge on sp2 carbon with plus charge. Very unstable, because first of all this carbon is electronegative. sp2 carbon is electronegative. Why it is electronegative? It need electron, because double bond is having what? It's having unsaturation, so it is electronegative. sp2 carbon is electronegative. Yes, sp2 carbon is electronegative. Electronegative carbon having positive charge means what? Very unstable. So this thing is what? Very unstable. What the reason is that positive charge on sp2 carbon. Reason for instability is what? sp2 carbon is having what? sp2 carbon having positive charge, very unstable. Hence here this is the answer for the question. Here it will not show not to show SN2, SN1. Now C option also we look why it is stable. One second. We're having benzene, it's benzylic. The Cl is going and we get a positive charge here, right? Look, stability at extreme, You know that in reaction mechanism chapter of class 11, you learned that benzylic carbocation is very stable. Hence this is very stable. So I have to ask you something. If they ask you if phenylic carbocation is stable, like not phenylic, this thing is there, somewhat happen and this will go SN1 reaction, it became like this. Here positive charge. Is this possible? Is it at least possible? SN1 reaction in phenyl is haloarene is possible? It is never possible. What? Because phenylic carbocation is very, very, very unstable. Reason positive charge on sp2 hybridized carbon. That's the reason for the B option also. That's the reason for instability of haloarenes towards nucleophilic substitution reaction. Very important. This is a very big theory. So the answer here is option B. Next question. Yes, 1 second. I went to copy the question. Sorry. 1 second. Yes. Here we have the next question. Identify B in the following reaction. The reaction is CH2 4 times Cl plus excess NH3. 1 second. Here what happens? We add excess NH3. Excess NH3 means we have the CH2 4 times here. What happens is that, no place for me to write this. 1 second. I'll keep it here. Okay. Yes. Yeah. Cl minus NH3 plus. We get here also the same. NH3 plus Cl minus. We get like this. Okay. We get like this. Because excess NH3 is coming. Excess NH3 means what happened? NH3 will give one of its lone pair to Cl. Okay, understood? Yes. Hence we get NH3 Cl. Now what happens is that we are adding NaOH. Both the Cl will escape, and hence we get diamine. We get a diamine as the product. NH2 plus NaCl plus H2O. No, 1 second. NaCl plus H2O itself, I think. Yes. So here the answer will be option 2. Okay, understood? This question is really from amines chapter, but it is having halogen in it also. So we add it in the haloarene chapter. Next question. Yes, I'll have the next set of questions here. Yes. Yes, we have it. Given below are two statements, one labeled assertion, reason. Assertion. Aryl halates cannot be prepared by replacement of hydroxyl group of phenol by halogen atom. So 1 second. Aryl halates cannot prepared by replacement of hydroxyl group of phenyl atom. Yeah, this is yes. So the assertion is correct. I'll explain it. 1 second. Assertion is correct. They are telling that, like, as we prepare ROH plus HX gives X plus H2O, we cannot prepare a haloarene by that method, like this. Plus HX gives oh my god, 1 second. haloarene, 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 haloarene plus H2O. This is not happening. This is not preferable. The reason for that is, I'm explaining it here. Look, this is our phenol. This is our phenol. Yes. Now we are having our phenol here. It's having 2 electrons with it. 2 electrons with it. What happens? Oxygen gives its electron here. Then this will jump here. Resonance. Look, resonance stabilization of this atom. Minus. So I am drawing all the resonance structures. No need of all resonance structures. I'll just draw this 2. You know that in alcohol chapter you have learned this resonance structures for board examination. This is very, 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 very important. Hence, look, what happening here? Look, OH and this C. This OHC, OC bond here is having a partial double bond character. Double bond character. Hence, here this OH and C is having a partial double bond character. It is tough to break the bond. Tough to break the bond because the bond is stronger. Double bond, strong bond. It's very tough for a halogen to come and attack there and break it. It's not possible. That is the reason why aryl halides cannot be prepared by replacement of hydroxyl. Oh my god. Replacement of hydroxyl group of phenol. This assertion is correct. Now the reason for that, phenol react with halogen acids violently. What? Oh, it's very what? Reason. Phenol react with halogen acid violently. The reason is that phenol will react with the halogen acid. It's telling that the reason for the above thing of why aryl halides cannot be prepared by replacement of hydroxyl group is that it will react like this to form something like this. Very nice. Very what? Unnecessary they are asking this question, I think. Unnecessary they are asking this question. For sure, if this assertion is correct, then this reason is for sure what false itself. Right? Because what we told the assertion is being contradicted by the reason. It's never an explanation. It's a wrong explanation. So the correct answer is assertion is true, reason is false. Assertion is true, reason is false. Now we are having the question number 8. January 29th, shift 2. Okay. Let it be anything. Alkyl halide is converted into alkyl isocyanide by reacting with. I'll just go to the first question we did. AgCN is covalent. Right. So what we did in our first question? Yes, AgCN. What happens? AgCN being covalent, only have nitrogen for bonding. Hence, AgCN plus Rx gives RNC, isocyanide, plus not RCN, plus AgCl. Yes, right. Yes. So, isocyanide is given by which one? AgCN. Option 4. Yes. So, these two questions were simple. Next, we will be going to the next question. Yes. Our next question is here. Yes. We are having a haloalkane, that is bromoarene plus Mg ether then CO2. Okay, one second. Mg ether then CO2. One second. Mg ether. I think we are going to get something. First thing is that Mg. So we get it as MgBr. MgBr. Right. Then CO2. One second. We think with CO2, we think that CO2 with MgBr, how methyl bromide. Yes, go to our you go to your carboxylic acid chapter and there something is hidden. Yes, I told you go to your carboxylic acid chapter. There you have some reaction called preparation of what? Preparation of what? Preparation of carboxylic acid from Grignard reagent. So in that we use carbon dioxide and H plus. What we get here? Yes, this thing will change into what? Benzoic acid. Yes. So this first step we get it to be as benzoic acid. Turn to benzoic acid. Now we are adding NH3 to it. NH3. When we add NH3 to benzoic acid, we get what? Amide. 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 So C double bond O, NH2. It's given in that same chapter itself. So we get here. After this we get a amide. What amide? Benzamide. Benzamide. Yes. Now last thing. Look. Bromine and NaOH. Where did I see bromine and NaOH? In which chapter? In haloalkane and haloarene. I don't remember anything with bromine and NaOH. Can I think something from alcohol chapter? No, it's not there. Go to your aldehyde chapter. Aldehyde chapter. You are having. So not aldehyde chapter. Sorry. In aldehyde chapter also nothing is told there. So in aldehyde chapter also it's not there. Then next chapter is carboxylic acid. There also it's not nothing related to the Br2 and NaOH is given. Go to your amines chapter. There's something called Hoffman bromamide synthesis. Bromamide synthesis. In that they use NaOH and Br. So here the third step is Hoffman bromamide synthesis. Hoffman bromamide synthesis, what's it? From amide we convert an amide to an amine. That is, the specialty of this reaction is the one carbon less. Remember it? Yes. So check here. Now we are adding bromine, Br2 and NaOH. This reaction is called Hoffman bromamide synthesis. Yes. So what happened after Hoffman bromamide synthesis? Yes. You're having this thing. One carbon less. So this thing, one carbon will be going and we get NH2. So our final product is what? Aniline. Our final product is aniline. So which one is aniline? Yes. Option 2 is the correct answer. So this is a very good question. It's having a mixture of organic chemistry chapters. Mixture means we went through what? Haloalkane, haloarene. Then we had CO2, carboxylic acid. Then we had amines chapter. Yes, a mixture. Yes. Here this question is not really from haloalkane and haloarene. This is a mixture of all chapters. So very nice question. Really very good question, right? So next question will be, we'll go to the next question. 1 second. Yes. Now we have our next question here. 1 second. Yes. Given below are two statements. So this is a statement type question. Statement 1. High concentration of strong nucleophilic reagent with secondary alkyl halide which do not have bulky substituent will follow SN2. High concentration of strong nucleophilic reagent with the secondary alkyl which do not have bulky substituent will follow SN2 mechanism. Okay, we'll search with the statement. 1 second. Next one. Statement 2. A secondary alkyl halide when treated with a large excess of ethanol follows SN1 mechanism. Look, SN2 mechanism and SN1 mechanism, the order is like for SN1 it is primary, secondary and tertiary. For SN2 it is primary, secondary and tertiary. Okay, perfect. Now the first statement is telling that high concentration of strong nucleophilic reagent with secondary alkyl halide which do not have bulky substituent will follow SN2 mechanism. That seems somewhat correct. Let us check. This question is somewhat confusing. Okay. Statement 2 is that, look, the statement 1 is telling that if there are no bulky substituent groups, secondary secondary alkyl halide will follow SN2 reaction. That's somewhat correct, because if bulky substituent groups are not there, transition state formation is very simple. Really, it is very simple, right? Yes. A secondary alkyl halide when treated with a large excess of ethanol follows SN1 mechanism. Ethanol and SN1 mechanism. Okay, I think 1 second, let me think. So when thinking I think that 1 second, yes, I got some I think that 1 second, sorry, yes. So statement 1 is telling high concentration of strong nuclei. So for SN2 reaction, it's having a direct proportionalship Rx and nucleophile. SN1 reaction only depends on the amount of what? Rx. But SN2 reaction depends on both Rx and nucleophile, right? Both Rx and nucleophile. So as nucleophile's concentration increases, SN2 reaction also increases. Here it's still high concentration of strong nucleophile. So hence statement 1 is correct. Because as so the statement 1, statement 1, the conclusion we get is that SN2 reaction is directly proportional to Rx, the concentration of Rx and the concentration of nucleophile. If nucleophile's concentration is high, that means SN2 reaction is preferable, is preferred. So statement 1 is correct. 1 is correct. Now statement 2. A secondary alkyl halide when treated with large excess of ethanol follows SN1 mechanism. Ethanol, the reaction with ethanol is a solvolysis. Ethanol is a solvolysis, right? Solvolysis. Ethanol is a polar protic solvent or polar aprotic solvent. You know, SN1 reaction happens in polar protic solvent and SN2 reaction happens in polar aprotic solvent. So polar is ethanol a polar protic or polar aprotic? Answer. Yes. Water, ethanol, ammonia, acetic acid, etc. are what? Ethanol, they are. Ethanol is a polar protic solvent. So excess of ethanol means the reaction is happening inside ethanol medium, right? Polar protic solvent. You know that SN1 reaction prefers polar protic solvent. Polar protic solvent. Excess of ethanol means medium is ethanol. Hence ethanol is a polar protic solvent. The reaction will be what? SN1. Hence the second statement is saying a secondary alkyl when treated with large. Yes, SN1. The reaction is SN1. So both the statements are correct. Both the statements are correct. Yes. So that's the answer for this. Now we are having 2 or 3 more questions. After that we'll end the session. Next we have, yeah, it's here. 1 second. Yes. Okay. It's a numerical question. Okay, nice. 2-chlorobutane plus chlorine. So 2-chlorobutane, 1, 2, 3, 4, 2-chlorobutane plus Cl2 gives something like this. So this Cl, one more Cl will come here, right? So one more Cl can come in how many places? 1, 2, 3, 4. These 4 places the Cl can come. So we'll draw that. Cl, 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 Cl. So 4 places the Cl can come. Now the question is that total number of optically active isomers. So these are the 4 structures, right? One second. Sorry. Very sorry. Yes, these are the 4 structures. First one is this. So is there a chiral carbon in this structure? Let us check here. No, because here there are 2 hydrogens, no chiral. Is this a chiral carbon? Yes, this one is a chiral carbon. So here there will be 2 optical isomers. Perfect. Now is there any chiral carbon in this structure? 2 means 2. They only ask optical isomers. Don't count other isomers and all. Okay, optical isomers. Okay, optical isomers. Here there are 2 optical, because 1 chiral carbon is here. 1 chiral carbon. First one we have one chiral carbon, so one trans and one cis is here, one cis and one trans is here, 2. Now the second one don't have chiral carbon, no chiral carbon, so no cis and trans isomer, no optical isomers. Third one, let us check, one here, it is here, okay. One second, let me check. Yes, here we have 2 chiral carbons, right? Here one is here, 1 2 3 4, 1 2 3 4. So 4 optical isomers. Here we have one chiral carbon, right? One chiral carbon, one chiral carbon, only one. Yes, one carbon, so 2. So we can add totally, I think 4 plus 2 plus 2, 8 optical isomers. That's the answer. Okay, I don't know, the question's answer is being shown as 6 isomers. I have a doubt in the same question. Let me check. 1 second. Sorry for my foolishness. I did a big mistake here. I didn't calculate it in an order because the formula of calculating optical isomer is not there in NCERT. So there's a small problem here. Look, in this one we had a problem. Okay, this one we had a problem. Others are perfect. Okay, others are perfect. So let us take only that one and I'll explain it. I knew it. I thought the same before doing it. There was a mistake in that thing. I thought, because look, in this compound there's a plane of symmetry. Really, this chiral carbon is there. This chiral carbon is here. Right. There's a plane of symmetry in this compound. There is a plane of symmetry in this compound. Right, plane of symmetry. Okay, right. I think that's the thing where we went wrong. We didn't consider the plane of symmetry. We should have considered it. Right, we should have considered it. Now, you know that there's a formula for the optical isomers. Optical isomers, that is 2 raised to n. 2 raised to n. In case of unsymmetrical. But here in this case we are having a symmetric isomer, right? Symmetric. This is symmetric. Therefore, for symmetric, if there are even number of chiral carbon, the formula is 2 raised to n minus 1. Okay. And if there are odd, it is in between. Someone came in my home, that's why I had a disruption. Sorry for the disruption. For odd number of carbon, it is 2 raised to n minus 1 plus 2 raised to n minus 1 by 2. Okay. No, not 2. This is the formula for number of chiral carbons. Okay, I hope you understood this. That's the reason why we went wrong. That is the only reason why we went what? Wrong. Okay. So now you can calculate using this. You please calculate. I'm giving you 2 minutes to calculate. Yes. So here the number of chiral carbon is even, right? So it will become 2 raised to n minus 1. That is 2 raised to 2 minus 1. That is 2 raised to 1. That is 2. Only 2 chiral carbon. 2 optical isomers will be in there in this case. That why this 4 we should cut and make it 2. Hence it will become 6. So that's the thing we went wrong. So please learn these formulas. Important. So optical isomers in unsymmetrical case. Optical isomers. Unsymmetrical is equal to 2 raised to n. Optical isomers, symmetric, even number, even number, 2 raised to n minus 1, odd, 2 raised to n minus 1, minus 2 raised to n minus 1 by 2. Hello. Plus 2 raised to n minus 1 by 2. Okay, that's the formula. Now we'll take the next question. We are only having 2 more questions in the session. Yes. 1 second, sorry. Yes, we have the next question, the last set of questions here. Yes. So the first one will be a numerical one. We are having two products, CH3, CH2, Br plus NaOH. With the C2H5OH, we will get one B. The total number of hydrogen in product A and product B. You find out. Yes. So first question, the product A we will find it out. CH3, CH2, Br plus NaOH in ethanol. Ethanol. You know that this we'll get it as Br will go, we'll get double bond. So CH2 double bond, CH2, something like this, right? Yes, we get this as the answer. Now product B. It's very simple, not that difficult. CH3, CH2, Br plus NaOH plus H2O. We get an alcohol, H2O. We get an alcohol. Because this is not an unsymmetrical carbon, it's a symmetric one, we get it like this. CH3, CH2, OH. Okay. Now add the number of hydrogen. 1, 2, 3, 4, 5, 6, 6. Plus here how much? 1, 2, 3, 4, 4. That is total 10 hydrogens. That's the answer. So 10 will be the answer. It was simple. Now the correct order for reactivity in electrophilic substitution reaction of the following. Electrophilic substitution. Okay. Look, for electrophilic substitution, NO2, Cl. Look, option C. First one, C. We'll check that because that's related with Haloalkanes and Haloarenes chapter, right? Cl. You know that this thing will happen. Resonance will happen. And what happen? We'll get a negative charge in para and ortho position. Right? Para and ortho position. Hence, Cl is very much electrophilic substituting. It supports electrophilic substitution. No problem. Now let us check A. A will be not that supporting to electrophilic substitution, but D. Look at D. D is very unstable with electrophilic substitution. D is a very strong minus I effect. Right? So that will not happen. So I think the option will be yes. So the answer will be, look, for a B it is having plus I effect and plus M effect, right? Plus I and plus M effect. So it will be having the most electrophilic substitution. So B will be having most electrophilic. So these two are wrong. Now look at option 1 and option 4. Option 1 is telling C is having next. The problem is that this is having minus plus M effect. It is having plus M effect but minus I. Here minus I effect dominates. So it is having some problem. Hence what happened? A will be more electrophilic substitution. Have a more electrophilic substitution compared to C. Because it is not having a minus I effect. Minus I effect is very strong in this thing. Minus I effect is strong. The problem is that electrophilic substitution reaction will be weak. So the answer will be option B. Anyway, this D is having both minus M and minus I. Don't think about it. It will have least. It's having minus M, both minus M and minus I. But C is having plus M and minus I. But minus I effect dominates. B is having plus M and plus I. Both the plus, it's giving. CH3 is a giving group, donating group. That way, no need to check. B will be having the most towards affinity towards electrophilic substitution reaction. So by this, the questions come to an end. We did many questions, approximately 10, 11, 12 questions. That was asking the January session of JEE Mains 2024. Now we are having the April session left that we'll be doing afterwards. Thank you everyone. Thank you for seeing the video. Thank you.